Alright guys, we're going to wrap up these videos here. We're going to do just 2 more pages, but these are kind of the more intense ones. So let's see what would happen. This first one, first we got a chain rule with a product on the inside, so we got a little bit of simplifying ahead of us, but really not too bad. Let's just focus on it one step at a time. So if we were to take the derivative of both sides, let's do the right side first. That's 0. That was easy. Okay, left side. We're going to take the derivative of the outside, which is cosine. Then we're going to multiply that times, or we're going to leave the inside alone the first time. Then we multiply that by the derivative of the inside, which if this is a and b, then you're looking at a times b prime plus b times a prime. Well, a is x, and then b is dy dx, so the b prime, the derivative of y with respect to x is dy dx. That's how we write that. Plus b is y, then the derivative of x with respect to x dx is just 1. So this might look like it's a complex multiplication, but it's really just distributive power. You're taking this outside term, multiplying it to the first one and the second one. So let's do that and see what happens. That means I'll have x cosine xy times dy dx plus y times cosine xy equals 0. So now if I were to kind of separate non and regular dy dx's, so this is non right here, we're going to move that over. That means that we'll have x times cosine xy times dy dx equals negative y cosine xy. So I'm going to divide by x cosine xy on both sides. Now something really cool kind of happens here. Do you see it? I see it. Those things simplify, but so does this. Cosine xy simplified on both sides. So the derivative of this is just negative y over x. That's really cool. Really, really cool. Sometimes to get a simple answer from a complex type function. Simple derivative, I should say. Alright, this next one, not too bad. In fact, we've done this pretty consistently where we have x squared plus y squared equals some constant. It's a circle type thing. So if I were to find the derivative of this, doing each term individually, we have 2x plus 2y dy dx equals 0, and then we wind up simplifying, we move the 2x over, and then we're going to get 2y dy dx equals negative 2x, and we divide by 2y, divide by 2y, and then we get negative x over y. Let's make that negative x. Keep it clean at least a little bit here. So this equals negative x over y. Now I need to remember this. You'll see why in a second. They just told me to find d squared y over dx squared. It's really like this, dx, quantity squared. Because what I'm doing is I'm doing the derivative ddx of dy dx. Now look at all the d's and the x's I got. I got 2 d's, so that's d squared y. And I got 2 dx's down low, so I'm going to put dx squared. And that's really what I'm doing. I'm taking the derivative of the derivative, also known as the second derivative. So looking at this one then, the second derivative means I got to take the derivative of what I just found. It's a quotient rule. Well, then let's do the quotient rule. D squared y over dx quantity squared is going to equal, I like to write out my little rhythm here, low d high minus high d low, square the bottom, and make a low low. Okay, low d high, that's going to be y times the derivative of negative x, which is negative 1, minus high d low. The high is negative x times the derivative of y with respect to x is dy dx. And then on the bottom we got y squared. Now the crazy is I have this dy dx in the middle of my second derivative, but I know what dy dx is. I have it right here. So I'm going to do a substitution. We're going to plug that in. That means I'll have negative y if I simplify that first term, plus, because I got negative, x times negative x over y, all over y squared. That's it. That is my second derivative, d squared y over dx squared. Excellent. Let's wrap this up with a couple of applications. The first one, find the equation of the tangent line. Tangent, 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 line, line, line means we got y minus y1 equals m times x minus x1. What do we have? We have a y1 and an x1 here, but we need the m. And remember that m is going to be the slope, dy dx, at 9, 4. Well, then we got to find the derivative and then plug in 9, 4. Let's do that. Remember this here, this is actually going to be x to the 1/2, and this is going to be y to the 1/2. That's going to help us as we work our way through. So the derivative of the first term there is going to be 1/2 x to the negative 1/2. The second term is going to be 1/2 y to the negative 1/2, but times dy dx, because we took the derivative of y, so we have some chain rule effect. This minus 1, that goes to 0, but then on the other side we also have a dy dx times 1, of course. So normally I move the non-dy dx terms, but this time I'll move this one over, just so I only really have to move one thing. That means I'll have 1/2 x to the negative 1/2, or, let's go ahead and simplify it. That would be 1 over 2 square root x. Now after I move that piece over, we'll have dy dx times 1 plus, now this term is going to be similar where it's 1 over 2 square root y. So I'm going to divide by that to get the dy dx by itself. 1 plus 1 over 2 square root y. So I divide by that over here. 1 plus 1 over 2 square root y. So if I want to find dy dx at 9, 4, that's going to be 1 over 2 times square root of 4, all over 1 plus 1 over 2 times square root of 9. Well, square root of 4 is 2, so that's 1 over 2 times 2, which is 1/4. And 1 over 2 times, well, square root of 9 is 3, so that's 1 plus 1/6, which is really 7/6. Now if I were to kind of simplify this, that's going to be 1/4 times 6 over 7, or 1/2 times 3 over 7, which is 3/14. Lots of fractions, but we love fractions. Okay, this last one, probably the biggest one of the day. A couple of notes that we want to keep in mind. Horizontal tangent lines. So when we have dy dx, which is the slope, so in other words that's rise over run, or the vertical over the horizontal. If our run equals 0, then that means that we have a vertical tangent line, that we are vertical. Vertical only. And if our rise equals 0, then that means that we are horizontal only. So that's what we want to keep in mind as we're going through this problem. So let's start by taking the derivative. Not too bad here. We're going to have 50x for the first term plus 32y dy dx, because it's chain rule, we took the derivative of y, plus 200 minus 160 dy dx equals 0. Now if I were to simplify this, we're going to move the non-terms over. So we have this dy dx here. We'll have dy dx times, well, we have a 32y minus 160 equals, and on the other side we're going to have minus 50x minus 200. So if we were to simplify this and get dy dx by itself, then we'd have 32y minus 160. So we got a numerator and a denominator. In other words, a rise and a run. So if my rise equals 0, that means I'm going to have a horizontal tangent line. And if my run equals 0, that means I'm going to have a vertical only, vertical tangent line. So let's see where the rise would equal 0 and the run would equal 0. So the horizontal tangent line is when the rise, or the numerator in this case, equals 0. Negative 50x minus 200, I'm going to make that equal 0. I move the 200 over, negative 50x equals 200. That means that x equals negative 4. So at x equals negative 4, I have horizontal tangent line. On the other side, for the run equals 0, that's my denominator. So I'm going to have 32y minus 160 equals 0. Simplify this, I got 32y equals 160. Now when I look at this, I know that there's probably a simple answer, but I like to simplify this first. I'm going to divide both sides by 16. That gives me 2y equals 10. Now it's pretty obvious. At y equals 5. So that means all across this function, when y equals 5, there's a vertical tangent line. And up on top and bottom of this function, when x equals negative 4, there's a horizontal tangent line. Excellent. Let's go ahead and stop there. Good job, you guys. Keep studying. Keep practicing. Good night.